item. And here a little overview about the topics today. So first of all, a little overview and comparison between previous mobile phone system. Then a little Wikipedia about 5G. What is the impact of 5G to measurement equipment? Why is the maximum exposure so important? Part 5 is I introduce to you and make a little sample about code selective measurements with the SRM 3006. And last but not least, FR2, that means frequency range up in the high gigahertz range, 24, 25 gigahertz. So here I will also show you some solutions. Overview in comparison with previous mobile phone systems. So the 2G, we had voice and short messages. Data was not really available. I think the data transmission rate was 9.6 kilobit per second, so really slow. But in terms of propagation, we already had the first MIMO, not massive MIMO, but MIMO antennas available. So the internet quality went a little bit better with 3G UMTS, and there we really could watch a little bit or surf a little bit in the internet with our mobile phones. This went much better with the standard today, the 4G, or also called LTE. Now we can watch YouTube videos, we can gamble games and so on. Also during that time, now at the end of LTE, there are the first 4G installation which have MIMO, massive MIMO beamforming antennas on board. You can see already massive MIMO has nothing really to do with 5G. It's an independent techniques of propagation. Okay. So, and also a lot of operators went over to software-defined radios. So that means 4G base stations was possible to switch it over to 5G services or dynamic spectrum sharing 4G and 5G within 120 megahertz signal by just a software update of the base station. So the base station became more and more intelligent and much more flexible. So the rollout of 5G was in parts just a software update, so a rollout by mouse click. 5G is now not only voice, it's also 4K, 8K video directly on your mobile phone. You have ultra fast mobile internet. You can now also use it for communication between machinery because it's ultra reliable and it has very low latency. We call it also Industry 4.0. We can also use it for car-to-car communications. It can maybe also one day replace the broadcasting. There are also running experiments about this. And parallel with 5G, there's also the rollout of the beamforming antennas. But as I said, they are independent. These are two technical independent items. When we look into the spectrum with the spectrum analyzers like the SRM, we can see the services here in different shape. And each of the four pictures has a span of 108 megahertz. And on the left-hand side, we see several operators using the 2G bandwidth. With 3G, a single operator needed around about 5 megahertz maximum bandwidth. With 4G, the bandwidth was rising already to maximum 20 megahertz. With 5G, below 6 gigahertz, the maximum bandwidth of the signal can be 100 megahertz. So more and more information could be transported, but it costs finally bandwidth. And when we look later on into the 24 gigahertz range, there we see bandwidth up to 400 megahertz for such a signal, so even more information. And when you see today a football stadium, like yesterday, yes, we did it, we won against France 2-1. When you look into a football stadium, here how many people are parallel watching another football game or whatever during the football match. You can imagine 60,000 people streaming. This needs capacity, and this can be only done by more bandwidth. So let's go a little bit into the wording of 5G, just explain some little things. So beamforming and massive MIMO. Massive MIMO. MIMO was, as I mentioned already, was also possible with 2G. So it means they had 4 or 6 antenna elements inside of such a transmitting antenna. Today we have 128, 256 antenna elements inside of an antenna, and they can be used for doing so-called beamforming. So that means the mobile phone antenna is not transmitting anymore for 120 degrees, but it can have a much more narrow angle. And with 6G, they will become even more narrow. But as I mentioned, massive MIMO is a new technology, but does not depend on 5G. So we will have a lot of 5G installation not using massive MIMO antennas. For example, all applications below a gigahertz. We have a lot of installation at 700 megahertz, for example, for countryside propagation. There we will not use massive MIMO antenna because at those frequency, a massive MIMO antenna will have a surface of several square meters. So you don't want to have an antenna with 5, 6, 7 square meters surface onto your rooftop. No way. Okay. So at the moment, the only massive MIMO antennas I know, they are operating in the frequency range around 3.5 gigahertz and higher. And massive MIMO is also used, for example, in modern Wi-Fi routers. Okay, some 4G installations are also using. So, and as I mentioned, 5G can also be used without this technology. Here, a little example. When you look from above, on the left-hand side, you have a traditional base station. Here, only one segment, which is transmitting. And here we have the propagation into one direction of 120 degree, and it's operating without beamforming. Okay, so everybody is getting the same amount of exposure. On the right-hand side, we have the propagation with massive MIMO or with beamforming, and you can see only who is requesting for it, he is getting an exposure to EMF. So in terms of environmental health and safety, I believe beamforming is a good thing, because who does not request for it normally doesn't get nearly any radiation. So here it's more efficient in terms of propagation to the people, but also more efficient in terms of output power. Because you can imagine, if I want to cover such a big area here without any diversification between the different operators, the base station here needs more output power. And here the base station needs less output power because it just needs to build up some small links. So they can also reduce the efficiency. They can make the base station more efficient by this. Another technique which was already available with 4G, but which is much more common now in 5G, is the TDD techniques. So in the past, for example, in 2G, FDD, the frequency division duplex, was used. That means you had two frequency channels. So on the y-axis, we have the frequency, and on the x-axis, we have the time information. And there was one frequency channel reserved for, in this case, light blue, the uplink, and one channel was reserved for the downlink. But when you look now how you communicate with a base station, the typical example is you request YouTube for transmitting a video, and then YouTube is responding, means with the downlink, it's responding with several megabytes. Okay, you send up some kilobytes and the base station is responding with megabytes. So the channel for the downlink was much more used than the channel for uplink. And when you look into the statistics of mobile network, this is true. And reserving the same channel bandwidth is not efficient. So by this, they built up now so-called TDD network, time division duplex networks. And imagine now we have again an operator who has two channels. Now the base station and the mobile phone can transmit at the same channel, and they can transmit in different time slots. So here you can see for the uplink, we have around about 5 time slots which are reserved for the uplink, but for the downlink we can use now 2, 4, 6, 7, 14, around about 15 different time slots we can use for the downlink. So that means we can shift now the relationship between uplink and downlink depending on what is needed. So for machine-machine communication, as we will use it in 5G, for example, maybe there the uplink is much stronger than the downlink. We never know. By the TDD system, you have the possibility to align the uplink and downlink use just by changing the time slots. It's only a question of communication between base station and mobile phone. Okay, so we get a flexibility by the TDD system. For us, for measuring the radiation, this puts us a little bit in trouble because in the FDD technology, we had a clear channel for the uplink and we had a clear channel and clear frequency for the downlink. So here we could use a traditional spectrum analyzer to distinguish between uplink and downlink. With TDD, it's not longer possible because the mobile phone and the base station now are transmitting at the same frequency, only at different time slots. This makes the measurement much more complicated, and here the code selective measurement is a big advantage. Okay, because the code selective measurement makes it fully automatic, taking those effects into account. So what is the impact of 5G on measurement technology? I mentioned it already. It's becoming maybe a little bit complicated. But let's first start with the personal protection of people at workplace. And here we can say, so those signal parameters, so the modulation and so on for 5G is equivalent to the modulation of 4G. And there are a lot of similarities. So we can say the signal parameters such as modulation, crest factor, bandwidth, signal shape is not critical for personal monitors like the Redman 2 and the Natalot S3, and also the broadband meter Fieldman or the older instrument, the NBM, they don't really care about 5G. Okay. As all those models operate also up to 60 or even 90 gigahertz, also the newer technologies transmitting at 24 gigahertz are no problem for them. And you should take care that you don't use any more equipment up to 6 or 8 gigahertz. This puts us a little bit in trouble in terms of the SRM. This can only work up to 6 gigahertz, but for him, we found a solution which I will show you in part 6. And as the beam is changing its direction, you should have your personal monitor always worn on your body. Okay. If you want to define safety zone, especially with beamforming antenna, this will become more difficult. Okay, because just standing out and measuring does not really help as long as you are measuring the traffic information, because maybe there is no traffic and then the base station is not transmitting. They are just transmitting a little bit their signalization, but the amount of radiation propagated by the signaling is much, much lower than the traffic information. So here, the best thing is to do a simulation. Okay, a rough estimation can be done by calculation, even by Excel. There are small tools which can do so by Excel, for example, or you can do it on a sheet of paper if you are familiar with antenna gain and so on. Precisely, you can do it by a simulation software like the EFC 400 telecommunication. And by them, you can define safety zones where it is not allowed to enter or where it is allowed to enter. Because especially in countries where we have low limit values like 3 volts or 6 volt, per meter, there those safety areas can be exceeded even by a mobile phone installation. So when we measure the current exposure, so what's on air at the moment, we can do it with, for example, the fieldman. Okay, so the fieldman can show, and if your measurement procedure is asking you just for the current exposure, use a fieldman or use a spectrum analyzer like the SRM, and they can give you the results in volts per meter and percent of standard. And the SRM even can distinguish between different operators and so on. And nowadays he can also measure at frequency range to up to 29 gigahertz. So they can even give you the result directly in percent of standard, as we see it here from the SRM 5G. The maximum exposure was 0.1% of standard. So all is okay. But imagine this is just the current exposure. And as I told you, now we also have beamforming antennas, means at the moment where you took the measurement, maybe there was no beam pointing on you. So there are some technologies, like for example, you use your mobile phone and make a speed test for the transmission. By this, you are pulling a beam towards you. By this, you can get the beam pointing onto you. This is a technique you can use, but it also has some disadvantages. We will come back to this a little bit later. But if your measurement procedure is asking just for current exposure, it's possible with an NBM or with an SRM, but it also has its problem. Better, I believe, is the long-term surveillance with an area monitor where you measure 24 hours, 7 days a week, and you measure this kind of radiation all day long, and you show the results directly into the internet so that public can see if they are safe or unsafe. And this is a very popular technique. For example, in Italy, there they have more than 2,000 area monitors installed. Greece has hundreds or thousands of area monitors installed. So in several countries, this technique is helping a lot to calm down the fears of population. So why is the actual maximum exposure so important? Why is it even more important for 5G? So this picture I've taken from an older standard where they described how the exposure or how the output power of a base station is changing versus time. And you can see here that here in this situation at 6 o'clock in the evening, they had their maximum. And 4 o'clock in the morning, there was nearly no communication. So in front of a discotheque, a base station in front of a discotheque on Sunday morning, this will be completely different. This will be completely opposite. So this picture should show the amount of radiation you can measure depends on when you take the measurement. Not only where you take the measurement, but also when you take the measurement. So for 2G, this was quite simple to solve because the difference between the maximum exposure and the minimum exposure was between 6 to 8 dB. This was not too much, and I remember we had measurement procedures saying, look, add 10 dB, and then you are on the safe side. If the value is still below the limit value, you are fine. You don't have to investigate more. But with more and more techniques and more and more experience, the base stations became more and more efficient. So here, even when there is silence, we still have a strong amount of radiation. This is changing now over the ages of the different mobile phone systems. And nowadays, with 5G, new radio, and beamforming antennas, we sometimes see a dynamic of the signals of more than 30 dB. 30 dB, who is not familiar with 30 dB, I would like to show it also in linear values in voltage or power. A linear value, 30 dB, means the factor 32. So that means you have to multiply your result. If you want to be on the safe side, you have to multiply your result not longer with a factor 2, but with a factor 32. Or if you measure in power, you have to multiply it with a factor 1000. So you can see the maximum is not getting higher compared between 2G and 5G, but during a time where there is no propagation or the beam does not point of you, there is nearly silence. Okay, so and when you are measuring in a silence phase, um, you measure nearly nothing. Okay, so the actual value, I believe, is not a good thing to measure for 5G with beamforming because the base station became more efficient, which is good, but puts some additional challenges to us who will take the measurement. So the measurement of the code to measure it now code selective with the SRM 3006 became much more important because the dynamic of the signal is so high today. So at the beginning of the code selective measurements in 5G and beamforming, we had a lot of problems to solve all those problems. Not we, NADA, but the complete community of EMF. And we solved it a little bit by making instead of one long equation with several variables, we divided in several equations. And the first formula then, which happened, was the code selective measurement. This was the first point which was defined. And this is exactly what the SRM is nowadays doing. So the code selective measurement is the base for the extrapolation. And by the measurement of the secondary synchronization signal inside of the PVCH block, it was found out that this is the best solution. And therefore, we nowadays have a mode inside of the SRM 3006, 5G mode, and this is measuring exactly the SSS. Okay, full stop. By this, we have the base for an extrapolation. Extrapolation, again, is a different formula. And in 4G and in 3G and 4G, the extrapolation was one simple factor, mostly. Here in 3G and in 5G, and especially with beamforming, we have three independent factors, and the factors depend on the location where you are just standing on the road. On one side of the road, you have a different factor than on the other side of the road. So it's becoming much more complicated. And when you're standing out on the road and people are watching what you are doing there, you normally get a little bit nervous. And we said, we don't want that you put those extrapolation factors into the SRM during you do the measurement, because you would do it, I believe, in the wrong way. So the extrapolation should be done later on in your office when you have a little bit of silence around you, because the extrapolation, especially to beamforming antenna, is so complicated. You need more silence to do so. So what we do with the SRM is just providing you the basic value, and the extrapolation should be done out, not inside of the SRM. When we go through the procedure, this means the basic result is the demodulation-based measurement of the synchronization pulse. This synchronization pulse is always propagated. The synchronization pulse can have also beamforming, but it's transmitted with full power. So that's why we can take him as a reference, okay? So it's not depending on the traffic. It's always transmitted with full power. That's why we take him as the base, okay? And this result is provided by the SRM, the SSS. So the next thing is, what we have to do is the measurement result we see there is just one little resource element we are measuring there. But the measurement signal is, especially the traffic signal, is much, much wider. So we now, first of all, have to extrapolate to the maximum bandwidth, so the maximum signal power, what is maximum possible, and then we can reduce it again by the second factor, the TDD factor. As I mentioned, TDD means sometimes the base station is transmitting, sometimes the mobile phone is transmitting, and we don't want to make here an unfair calculation. We just want to measure the amount of the base stations, and that's why we have to reduce this 100% time consumption, which we have here in the extrapolation to the maximum power. We have to reduce it by the TDD factor because the base station does not transmit all the time. Okay, so we have here a factor 2, and the factor 3 comes from the beamforming. If beamforming is in use, maybe the base station is using a different antenna setting for the signalization than for the traffic. And the traffic can even have a much more narrow beam with higher gain. This means that the traffic signal can be transmitted with higher exposure values. This means when we measure the signalization signal, we underestimate. And we have to add something to our demodulation signal that we also get the maximum power out of the traffic beam here. Underestimation is not acceptable if we talk about safety values. Okay, so the beamforming here puts an additional third factor, but in a positive way. So it will make the result higher. The TDD factor can only make the result lower, but this can make the result higher. So this is why it must be taken into account if we want to measure it in terms of health and safety. So after those three factors, we have the final result. So when we do the SSS measurement with the SRM 3006, so this measurement, the measurement itself is independent of the traffic situation because we are measuring the signaling. It can even distinguish between different cells, between different operators, and it does not react to the emission of a cell phone. This is especially important for TDD systems. And remember, 5G in higher frequency ranges will mostly use TDD systems. Okay. So the extrapolation to the maximum exposure means you will have a watertight result. Remember, with 2G, you just added the factor 2 and you had a watertight result because even when you measured as a minimum point, you multiplied it by 2, the base station was not able to transmit more. Okay, your result was watertight. Now we have to multiply in terms of power with a factor 1000 to have a watertight result. And especially in country with 3 or 6 volts per meter limit line, you will exceed the limit value. So you cannot do with an actual measurement a watertight result. You can only do it with a code selective measurement or a measurement which is doing the extrapolation to the maximum value. Okay, but more precisely than just taking the factor 1000. So let's have a look how it looks like on the SRM. If we do such an extrapolation here on the left-hand side, you will see where we are in our block diagram. So at the moment, we are at the demodulation-based measurement of the SSS. And you can see we have here an SRM. And he is measuring a maximum value for the cell ID number 8. Cell ID is like the street name and house number of the base station. So cell ID 8 is transmitted by the base station. I'm the sector antenna number 8, and the maximum is here quite low, 2.091 millivolts per meter. One topic you have to set here also is a SES. and this is here 15 kilohertz. So for frequencies below 7 gigahertz, we have 15 kilohertz or 30 kilohertz, which we can set. We will see it in the next slide why it is important. So this is a so-called subcarrier spacing. So it means how many carriers do I have here? And what the subcarrier spacing is telling us, which is the distance between two carriers. So as I mentioned, for the signalization, we can have two different ones. We can have 15 kilohertz or 30 kilohertz. And when we look now to our system here, we have here around about 20 megahertz system. So you can see the SRM has a span of 20 megahertz, and normally you say roughly this is a 20 megahertz system. In reality, it's an 18 megahertz system. And if you want to do the first rough estimation, this means we have 20 megahertz divided by 15 kilohertz. So the value we see here is just the value of one resource block. It's not the entire SSS, it's just one resource block of the SSS or one resource block of the entire system here, okay? And the system runs here, roughly calculated, 20 megahertz divided by 15 kilohertz is around about 1,300 resource blocks parallel. If we want to know the value exactly, we go into the IEC 62232, and here we find a table inside which is telling you with a subcarrier spacing of 15 kilohertz and the 20 megahertz or 80 megahertz system, we have 1,272 resource blocks running parallel. So by this factor, by 1,200, we have to multiply our result to have the entire power here over the whole bandwidth which is reserved for this service. So this was the step number 2, the extrapolation to the maximum signal power. So this means now we have, if we just do the multiplication by 1200, we have the system which is running all the time with full power and all the time. Okay? But we learned we can have a TDD system. That means that maybe only 80% of the time the downlink is used and the uplink is using 50% and maybe 5% are used for a guard interval. Okay, so if FTD, so there is no TDD, if FTD is used, this factor is 1 because then the base station is allowed to transmit all the time and it will do so. Okay. 3GPP is telling us that for 5G there are 61 predefined symbol combinations allowed. So up to now I didn't find a system which is changing it dynamically. Many times an operator is using it. They will switch it for the entire country to a special relationship, as I just mentioned, 80% downlink, 50% uplink. In Germany, it's even more simple. There, the mobile operator talk to each other, and they said, look, we all transmit at the same time and we all receive at the same time. For signal quality, we don't want to have the situation that, for example, T-Mobile is transmitting, the base station is transmitting, and Vodafone is receiving at that time. This could cause interference if there is any kind of PIM or something like that on the air. This can cause problems. So they say we don't use this flexibility, but in terms of better service, we all synchronize our services and we all use the same uplink and downlink timing. So this factor is not the big thing here in Germany. And remember, you just can take the factor 1. More than 1 is not possible. You just can reduce by the TDD factor. So for lazy people like me, just use the factor 1. Okay. If you want to measure the TDD factor, in principle, it's possible, but practically nearly not. Okay, but I've, I've, I've tried it with a 5G system, and here you can see if there is low traffic, here it is nearly impossible, and this is a measurement versus time. There is no possibility to see when does the base station transmit and when does the mobile phone transmit. Okay, therefore we need a situation where we produce 100% traffic, like I did it here on the right hand side. This was done with a special software, and this was only possible due to the fact that at that time nobody was using parallel 5G services, because otherwise you will never have 100% attention by the base station for your test, because the base station also has to serve other mobile phones. Okay, so such an ideal result will not happen when 5G is really in use. So the easiest way is really to do such a measurement. For example, put your alarm clock to 3 o'clock in the morning and do a measurement, such kind of measurement at 3 o'clock in the morning with a test software on your mobile phone, or ask your operator which TDD factor they are using. Or as long as you are below the limit value, just take the factor 1. Okay. A beamforming factor is a more difficult one. If there is no beamforming or steering on air, the extrapolation factor is again simply 1. And you can see it already on the SRM if beamforming is active or not active. So if beamforming is active for the traffic signal, normally it's also switched on for the signalization. And if it is switched on for the signalization, you will have several SSS numbers here, not only one, but you will have here 1, 2, 3, 4, up to 8 SSS on air. And normally when you have here some strong values, you will see here a figure like 6 or 7. Okay, so if all values are like here 1, you can be nearly sure there is no beamforming, so no worries. Or if you are at 700 megahertz, you can be sure there will be no beamforming. Keep the factor to 1. You can even make an optical testing if you don't have such more square housing antennas onto the pylons, then you can be sure if you just have those traditional tall ones on the tower, you can be nearly sure there is no beamforming, because beamforming needs such, or the shaping of the new antennas is more square. If they are not there, you don't have beamforming. Just take the factor 1, that's it, done. Okay. I would like to do for our example the final calculation. So we take the value, the electric field strength for the ESS, the 2.1 millivolts per meter, multiplied by the root out of the extrapolation factor to total power, 1272, multiplied by the TDD factor of 0.8, multiplied by 1, because there is no beamforming, is a result of 66.7 volts per meter. So as the value was here already low, the total result is also low. But remember, we have here a factor of 1000, okay? So even values which are here low, some 100 millivolts, can be much higher when we do the final extrapolation, okay? Beamforming, I don't like to do an example today, because beamforming is a topic which is much more complicated. And first of all, most applications will not have beamforming. They use the conventional antenna technology, and it's not necessary. So massive MIMO or beamforming requires a separate consideration, and this is far beyond the scope of this little short PowerPoint. This really needs a separate webinar, but there are also trainings, and in the near future we will also have such an application note available. So this was a paper which was or an article which an experiment which was published for the IEC 62232, and we will send it out soon or make it available by our web page, and this application note is available soon. This is describing a little bit the techniques on beamforming antennas, how the extrapolation can be done also with different measurement examples, like, for example, with measurement of the code selective and time selective measurements and so on. So here you will find a lot of more information. Plus, we will also have a seminar here at NADA. I will show you later on a little bit. We will have seminars here at NADA regarding measurement with the SRM, and one special day just talking about 5G measurements, okay? Because this is more complicated. But I mentioned it already, 5G will not stop at 7 gigahertz. They will even extend to higher frequency ranges. They will have services at 24 up to 52 gigahertz frequency range. And here, this will change also our measurement strategy. So with the SRM 3006, we were able to cover all the frequencies up to 6 gigahertz, and you can see already the first services go up above 6 gigahertz. They put us today a little bit into trouble, but we are working on a solution. Much more important was the range 24 to 30 gigahertz, because, for example, in Australia, we have a strong rollout of systems working in this frequency area. And this frequency area we are covering today already with the SRM 3006, because we made a special or two special antennas for him with down converters inside, which can translate those frequencies so that the SRM 3006 can measure them. So there is no hardware modification necessary on your SRM 3006 to extend the frequency range up to 27 gigahertz. So when we look to the propagation of those kind of signals in the high gigahertz range, the propagation is very different. So 700 megahertz propagation goes through a building without big problems. Okay, so but if we have a 25 gigahertz system, even a window is already a barrier for such kind of signals. In Australia, they measured values up to 30 dB, means a factor 1000. Remember, 30 dB, factor 1000 reduction of the signal just by a simple window. Okay, so the behind a entire building, there is nothing. Okay, so when we look through the propagation distance, and if we have here a 5G base stations working on 700 megahertz, we can cover an area of around about 10 kilometers. Okay. To higher distance, the propagation is not good enough. When we have a 2 gigahertz system, it can cover an area of 2 kilometers roundabout. A 3.6 gigahertz system, we can look after an area up to 1 kilohertz, sorry, not kilohertz, 1 kilometer, and with beamforming, it can extend the range up to 2.5 kilometers. Okay, so beamforming here is an advantage. And when we look to 25 gigahertz, so this can just make 300 meters. With beamforming, it can be up to 1 kilometer. So we can look after a building, we can look after a block, but we cannot look after, for example, countryside areas. Okay, no way. So the highlights of these kind of down converter antennas means you can extend the existing SRM 3006 to a frequency range of 24 to 29 gigahertz without hardware modification. The only thing you have to do on the SRM is you have to make a software update. You even don't have to have any kind of software option or something like that. The antennas are calibrated. All the calibration factors are inside of the antennas, automatically transferred into the SRM, like you know it from other SRM antennas. You can measure the values in percent of standards in milliwatts per centimeter square. They are as easy as the other SRM antennas, and the SRM basic unit also takes care about the frequency offset. So that means you read 24.5 gigahertz on the screen of SRM. Simple, absolutely, to operate. But as you can see, we created two of them. Why do we have two of them? So one of them is a traditional horn antenna. So when we talk about those frequency ranges, mostly the antennas are horn antennas. They look like this. Here I've taken away the foam cover from the antenna. And as you can see, this is not only looking, it is a real horn antenna, and uh, its most sensitivity it will have into the direction of the horn. So this is like, let's say, like a laser pointer. It's pointing into one direction. There it can measure. Okay, full stop. From its technology, the omnidirectional antenna is also a horn antenna from the technology, but it's not shaped like a horn, but it's shaped like a donut. And this is also the receiving characteristic. So it's 360 degrees around it, but not to the top and not to the bottom. Okay, so it's not isotropic, it's omnidirectional. So it's not receiving in three axes, it's only receiving in two axes. We couldn't find a solution for isotropic antennas, so we said omnidirectional is the best compromise. Okay, so because in many cases you don't have to measure into the air or to the ground. So that's why we have this omnidirectional antenna also on board. So why do we now have, here again a little picture. So we measure with the omnidirectional antenna. When you point into the sky, we measure on X and Y axis, but not on the Z axis. So if you really want to make an isotropic measurement, it is possible. You need, for example, one of those antenna holders, and maybe from other not isotropic antennas from the NADA portfolio, you know the sequence inside of the SRM 3006, which is guiding you through three manual isotropic measurements, and this will automatically add the three manual measurements together, and that you have an isotropic result on your SRM again. So this is also working with the SRM 3006. So there is a procedure inside, but I believe mostly it's not necessary. Just take the antenna, point towards the sky, maybe change the angle a little bit, switch it to max hold, and this is mostly good enough. Why two antennas and when to use which of those antennas? So this depends a little bit on the application you can have. If your application is you have to do the acceptance test of the base station, okay, you are, let's say, authority and you have to make the acceptance test of the base stations, or you are the operator and you want to know what is my base station. Then the directional horn antenna is, I believe, the better approach, because you can point directly to the antenna and all propagation from other antennas of the same operators maybe also are excluded by the sensitivity of the antenna, because it's only measuring in one direction, full stop. And even you don't have any problems with the pickup of other cell phone users, because they don't transmit into your direction. Here, the omnidirectional antenna is not a good approach, okay, because it will pick up also if you want to make here T-Mobile antenna base station acceptances, it will also pick up from all the other T-Mobile antennas the radiation, because they are all transmitting at the same frequency, and also of all users of T-Mobile telephones which are running around there. It will pick up everything. Okay, so here for acceptance tests, the best solution is a directional antenna. This is different if you want to measure the total exposure. You are invited to measure, for example, the total exposure on the marketplace of a city of Berlin. Then you put your, let's say, the omnidirectional antenna onto the tripod and measure, for example, 6 minutes with max hold or whatever your measure procedure is telling you. And then the omnidirectional antenna is really the best solution, okay? Because scanning to all direction with the directional antenna is very, very time consuming, okay? And especially if you want to do a real isotropic measurement, a real isotropic measurement with an opening angle of even 40 degrees is extremely complex. Nothing for lazy boys like me. There you can use really the omnidirectional antenna for the SRM and the holder and the procedure inside of the SRM, and you will get really an isotropic result. So you can use nearly all modes with new antennas like spectrum, level recorder, scope, safety evaluation. What you can't use is the 5G demodulation mode because the subcarrier spacing in this frequency area is too wide. Measurement use cases I can show you also in little videos here, which were provided by Mike Wood from Tesla, because Tesla already has made a lot of installation in this frequency range. Here in Germany, I don't know any of them. And but luckily, Tesla made those experiments with first prototype on antennas from our side. Nowadays, we can deliver those antennas, and Mike Wood has provided us some videos which I would like to play. There are much more videos available on our YouTube channel.
Hi, it's Mike Wood from Telstra here. We're actually on top of the 5G Innovation Centre rooftop. This is an area where it's been quite common to use these new NADA millimetre wave kits when you're climbing a tower or when you're assessing an area for safety. So in this scenario, we're looking at the air conditioning plant and we're looking at the access areas below the tower. Now, I've got the horn antenna, so the omnidirectional antenna, I only need to use one probe, but with the horn antenna, which is this one, I'm going to need to use this probe and take two separate readings. I'm going to have to take one polarity and then rotate it and take the second polarity. So the first one I'm going to do, I'm going to run a speed test and I'm going to reset this, and that's reset. Once it gets going, now you'll start to see the energy picking up from the tower, and I'm measuring the actual level. I've got one polarization. When that finishes, I'm going to hit the hold button and integrate it. It's just about finished. I'll hold there. I'll go evaluation, integration, and I'm measuring 0.0035. So remember that value, 0.0035. What I'm going to do now is hit save, and that's saved it. Okay, so I'm going to escape out of this, or unhold it, escape, change the measurement range, and then do a reset once I hit my speed test. I'm running another speed test. I'm going to hit the reset button but change polarities. So now I've got the other polarization, and once it's finished reading its downlink, I'll push the hold button and it's pretty well finished. I'm going to hold that, and now I'm going to do an integration. So evaluation, integration, and we measured 0.00412. So we have to add those two values together to give us the actual power density or the actual field strength relative to the standard at this location.
So maybe some little comments towards this measurement. You can see he is using here a computer, and here we can see the modem, and by the modem he is pulling the beam from the mobile phone antenna towards his location where he is measuring, so that he really gets a strong signal here. And he is making here a modem test with a bandwidth of around about 800 megahertz bandwidth. So, but this is only working really when you are alone on air. Okay. And normally I also don't do those two measurements and add them together. I'm a little bit lazy. I put the instrument into max hold and um, turn the antenna a little bit. Okay. Here another test he did down in the road, and he did it now with the omnidirectional antenna. Yeah, I switch on again the tone.
So this is the omnidirectional antenna, ideally used for when we're measuring small cells, a millimeter wave like you can see in the background. Now this antenna actually has to be orientated vertically to pick up the most signal because it has a donut-shaped pattern. Now, Phil, if you want to show what the pattern looks like, it has a minimum if you're pointing straight towards the small cell. So if I was pointing towards the small cell, I'm actually reading a null. I have to rotate the antenna up so that it's picking up the maximum level. And through our tests, what we've found is it's about a 5 to 10 time difference between pointing straight at the small cell and holding the antenna up. Now this is probably going to be ideal for when you're on site doing compliance boundary tests, or if indeed we're checking the background level of small cells like we're here today. So I'm holding the probe up, I'm moving it around to get a peak reading, and as we found before, when we compared it to the horn antenna, the results were very close. So that's what we're doing here, testing millimeter wave 5G live in Melbourne using the new NADA 26 gig probe.
So thank you very much, Mike Wood, for this short videos. Very, very helpful. So as I mentioned on our YouTube channel, there are much more videos available. There is also in more details part 1, 2, 3, 4, and 5, yeah, about 5G measurements. Plus, if there are new ones, we will put them also onto our YouTube channel, and you can stay informed, for example, by subscribing to our YouTube channel, to the LinkedIn channel, or to our own news blog, where we, for example, just show that the adapter for NBM probes for the Fieldman is now available. Okay, so this is all information you will find on YouTube or on our own homepage. Plus, I mentioned also already, we have a training and application training on the topic 5G in general about SRM, which is very interesting. During the last year, I joined it 2 or 3 times by Professor Buschek. He has a lot of practical experience, and this kind of training can be done here in Germany. It's done frequently in Germany. You can go to our homepage and you can directly sign up there for the training. Or if your whole company, for example, is interested, or you've put all your operators of your country together into one room, Professor Buschek will also come over to your country.